Hello students, today we are in lecture number 54 and we will start today with torque. If we will place a current carrying conductor or loop inside uniform magnetic field, it experiences a torque that we will study today. It is lecture number 54. Chapter 4, Moving Charge and Magnetism of NCERT. My dear student, when we placed a current loop, it has the number of sides. Then due to the force on different sides in different direction, that is the couple of force, rotate the coil, and we know that if any body or the particle rotating, there must be some torque. Without torque, no body can rotate. So here we go with the topic. Its name, torque on current coil. Torque on current coil. Okay, placed in uniform magnetic field. All right, my dear student. Yes. Suppose this is a current loop. This is a coil and so the current is moving. Let me supply here with the battery. The current is going up and finally current is coming down. Here the current, let me change the direction of current so that the force will be easy to see. Here current is coming in this way. This is current. Now something you have to consider over here. Suppose this is the magnetic field in which this coil is kept. This magnetic field is B. We'll consider the direction also, my dear student. Here this side of the coil is B, this side is L. All right, length is L. Is very quite clear. The area of this coil, the face area will be L times B. All right, now current loop is placed in magnetic field, remember, so it will experience a torque on different arm. Why? Let we find the force on the different arm first. Remember students, this two arm, this arm and this arm, you can see is parallel to the magnetic field or anti-parallel to the magnetic field. Let me give the name. This P, Q, R and S. Side PQ, it is perpendicular to the magnetic field. Of course, it will experience some force. Side RS is also perpendicular to the magnetic field. Of course, this will also experience some force. But here you can see this side QR is anti-parallel. Current element in this way and the magnetic field in this way. So it is anti-parallel to the magnetic field and the force will be zero. Here again, for this element, we suppose this element is out of the field. This element is kept inside the magnetic field and it is parallel to the magnetic field. That's why the current will be zero. It means this two arm only QP and RS going to experience some force, and if both the arm will experience force in opposite direction, that is the couple of force, this coil start rotating. Suppose this is coil, one force acting in this way and another force acting in this way, okay, downward. one downward and one upward. So what will happen? This upward force will try to pull this one like this way, and the downward force will try to rotate the coil like this way. All right, so it will start rotating, okay, in this manner. Now uh, let me find here the directional force. Okay, but we know the force on QR and force on PS will be 0. Why, my dear students? Since theta is either 180 degree or 0 degree with the magnetic field, and parallel anti-parallel conductors never experience any force. Force on PQ. Okay, let we find force on PQ. All right, we know that the formula of force, it is I love sine theta. So F will be I, the direction of current. L, the direction of current will give the direction of L, and it is L minus J cross B. Magnetic field, it is for both the arm, it is BI. What will be minus J cross I, my dear student? Here, this is the direction of minus J, that is L, and magnetic field in this direction, so you have to put the finger in this way, cross one. It will goes up, that is I, okay, L, B, K, cap. This is the force. All right, my dear student. So you can represent the force in this way. Represent the direction of force. This coil experiencing the force in this direction. Okay, yes. Now force on this arm, that is RS. Force on RS. Again here the F, it is I, L, direction it is J cap, cross B, again I cap. So this will be the I, L, B, and the direction, this is the direction of L, and the B you have to move this way, so you cannot put your hand in this way, you have to flip it, and the direction of force will be downward, minus K. Minus K, this is the force. Now try to represent the force using this red marker. This is the direction of force. Now you can see, my dear students, on this arm force is acting in upward direction, on this arm force is acting in downward direction, so the coil will start rotating in this way. Let me draw here the axis. If this is axis, the coil will start rotating in this direction, and if it is rotating, it means there must be some torque. Okay, am I correct? Yes. Now our aim to find the torque. Remember, we know that the torque is R cross F. All right, here the two forces are there, so the two torque will act. Let me draw this one. From here it is rotating, so this will be the axis of rotation. Try to recall what you have studied in standard 11 about the rotation, in rotation about the torque. Okay, this is the axis of rotation, so this coil will rotate, and arm length for the rotation will be this way. If this is the B, okay, if this is the B, then what will be the arm length? It will be B by 2. All right, and for this force also, the arm length will be B by 2. We always take the direction of arm length, that is the R, from point of rotation to the application of force. So here we can write the net torque will be tau 1 plus tau 2. The two forces will act, the two torque will be considered here for this force. Okay, R, it is B by 2. B by 2, the direction it is minus I, cross F, and this F, it is the first F in PQ direction. This was F. Let me write the F1 and F2 so we will not confuse. This is the F1 and this is the F2. Alright, both the magnetic having same. ILB K cap. ILB K cap plus the second one, it is B by 2 R cross F. So this is the B by 2 and the direction I cross, the force it is this one, ILB minus K cap. Alright, now minus I cross K, minus I cross K, you'll find this is the minus I and cross K, it is upon, sorry, minus I cross K, this will be the J. So ILB by 2, ILB by 2, ILB by 2 and small b also, direction it is J cap plus this is the same ILB by 2 and the direction remain same. You can find out I cross minus K. So overall we are having here the 2 will be cancelled out. So ILBB, ILB times B, direction is J. Okay, this one. Now let me simplify. Finally we are towards the answer. You can see, my dear students, this L times B is nothing but the face area of the coil. Okay, face area of the coil, that is A. So this net torque can be written as IAB. IAB. Alright, IAB. A is the face area and the direction remains same. Here A is L into B, this is the face area. Now my dear students, suppose if we give the number of turns to this coil, okay, number of turns here, the number of turns if we will give to this coil, then which quantity will change? Giving the number of turns in this coil, remember only the magnetic field is going to be changed. Remember, the current is not going to be changed. The same current, because in series all the turn are given in series, so the 5 ampere current is flowing, suppose, then remain same in each turning. Alright, area is also not going to be changed. So because the radius will maintain, the length and breadth will maintain the same. So area is not going to be changed, current is not going to be changed. So magnetic field will change. If this one is making 1 Tesla, then another one also will make 1 Tesla. So the 2 Tesla will be equivalent. So magnetic field is going to be changed. For N turn, what will happen? The torque can be written as the N times will be B. So I, A, B. Okay, and this is the very important, my dear student. The same thing we'll use in galvanometer. Well, we'll start galvanometer. We'll study this particular thing, which is very important. Okay, now we are going to write this equation in vector form. Look at here. Here in vector form, tau can be written as this. Actually, this is in vector form. We are going to change this form. IA, try to recall this. IA was considered as the magnetic dipole moment for any loop, magnetic loop, or an IA. This is called the mu. Alright, and mu B and Z. You can write here mu B sine theta also. Here is 1. So the mu B sine 90 degree you can write, because the mu is, this current is flowing this way, the mu is perpendicular upward. So the angle between magnetic field and mu, it is 90 degree. So this can be written as, my dear student, as mu cross B. Remember, this is mu cross B. This is, and the magnitude is NIAB. Its magnitude is NIAB or mu b. Okay, mu b or NIAB. Okay, you have to remember this one. This is the magnitude of torque which is acting on the current loop, my dear students. Okay, now we'll try to find out if we place a dipole, that is the magnetic dipole, inside magnetic field in equilibrium. All right, here you can see it's rotating, but what will happen if after rotation it comes in this position? It will stop, it will not rotate. All right, so to disturb this coil from its equilibrium, this will consider the equilibrium position. When its plane surface is perpendicular to the magnetic field, it will be considered in equilibrium position. Okay, now from its equilibrium position, if you want to disturb this coil, it means we have to do some work, all right, to rotate this coil. We are going to find now here what amount of work we have to do to rotate this coil by theta angle, okay, by certain angle. So our next topic will be work done to rotate a coil. Work done to rotate a coil, yes, in uniform magnetic field. Inside uniform magnetic field, if you want to rotate a coil like this way, suppose this is the magnetic field provided and this is in stable state. This coil is perfectly in stable state. This is the direction of mu. You can say this is the direction of magnetic field. Both are the vector quantity. This is in a stable state perfectly. So to rotate this by some angle theta, suppose we rotate and mu comes in this direction to rotate from theta. Okay, so the first will be 0 degree to theta. We are going to rotate from 0 degree to theta, from 0 degree to theta degree. What we have to do, work, we are going to here find out. We know that work done by the torque, it is dw tau d theta. We have studied in standard 11th. dw equals to tau d theta. Okay, we'll integrate and we'll find the answer. It's very simple. So the dw tau that we have studied already, it is mu b sine theta. You can see here. So the mu b sine theta into the theta, from theta 1 to theta 2 we have to rotate. Let me take, let me wrap this one, my dear student. Okay, now I hope that you can now find the result, but let me help you. dw will be the w. This is also considered the potential energy in coil inside magnetic field. Remember, this is also called the potential energy inside magnetic field. Okay, my dear student. Yes, dw, that's w, because the change in work done gives the potential energy. Here the work is changing, so the total amount of work done to change the orientation, it is stored in as potential energy. Mu b is the constant taken out. Sine theta will be, integration of sine theta will be minus cos theta from theta 1 to theta 2. Alright, so we can write mu b minus cos theta 2 plus cos theta 1. Alright, yes, so it is mu b cos theta 1 minus cos theta 2. Okay, now try to find out. If you want to rotate the coil from the first angle, that is 0 degree, to some certain angle, then what will be the magnetic field? It is the mu b cos 0 minus cos theta. Okay, my dear students, cos theta. Okay, So this will be the mu b 1 minus cos theta, and this is the work done to rotate a coil inside magnetic field. Which type of coil? It is the current carrying coil. Remember, I have not mentioned everything in very short space, but it is the current carrying coil. Okay, my dear students. Now, we'll proceed for the next topic of our syllabus. It is, okay, before proceeding the next, let me solve a very interesting question. Okay, yes, my dear students, I'm giving you this question to solve. This is class 4. Although I'll solve, remember. Suppose this is the length of conductor L. This is, you're having a conductor of length L. If you bend this conductor in circular form, it will have the number of turns, suppose N. Okay, this very long conductor, and you have to bend this conductor in N number of turns. Finally, N number of turns. All right, how many turns you have given? N number of turns, so that it maintains some radius. Of course, there will be some radius. Okay, this is how many turns should, remember, listen carefully, how many turns, okay, should it have for maximum torque? How many turns you will give so that it experience maximum torque? And also you have to find that torque. For tau max, you have to find the number of turns. All right, and also you have to find the torque, that is maximum. All right, here I current is passed, it is given current passed through the conductor. What are given? You are having the length of the conductor, it was L, and this particular length is being winded to form a closed loop, the tiny closed loop. Okay, the number of turns it is given N. You have to find how many turns you will give. All right, remember the complete turn you have to give. How many turns you will give? It means the answer of N will be perfect number. It is 1, 2, 3, 4. Okay, integer. Now, how to think this type of question? What will be the answer? Try to think, my dear student, by yourself. Okay, and then I'll solve this question. My dear student, suppose to find the torque, what we know that here, torque, it is NIAB sine theta. The first thing, if you want the torque maximum, this theta should be such that sine theta maximum, of course it is 1. Sine theta should be 1. All right, of course it should be the perpendicular. Now the maximum torque, it will be the NIAB. Here I is the current, all right, N is the number of turning that we have to find actually. A is the area, remember. Here A is the area, which is pi r square. Okay, this one is the face area, but we don't know the value of r. So try to find out r. Since this L length gives the 2 pi r, but how many turns? N turns. So the N times 2 pi r. This L is N times 2 pi r. So you can find out the value of r from here. It is L by 2 pi times N. Very simple. Now you can find the area also. This area is pi r square, and this r, it means L square divided by 4 pi square times N square. It means this A will be L square divided by 4 pi, thus pi will cancel out, N square. Am I correct? Yes. Be careful while I'm solving any question. Be careful, my student. Now, we got the area. We are having the current. We have to find the number of turns. we are having the magnetic field. So the torque we can write here, it is N I B, and A it is L square by 4 pi N square. What we can write here, the N will be cancelled out, so it is L square IB divided by 4 pi times n. You can see the torque is L square IB by 4 pi n. Now try to find out the constant's value. L, could you change? No, you cannot change. It is given. The length of the conductor. I, could you change? No, you have given. Okay. Actually, the condition asking for the number of turns. So you are not going to change this current. For any value of current, you have to find the number of turn. Magnetic field, it is given. 4 pi already constant. It means the number of turn, you can see maximum the number of turn, the torque will be minimum. And minimum the number of turns, you will get the maximum torque. It means for tau max, okay, this n should be minimum. And how many minimum turn you can give? Minimum 1. 0 is has no value. All right, in turning, so the minimum you can give, you cannot say 0.5. Half is not perfect turn. Okay, so this n should be 1 for maximum torque. All right, so this is the answer. The number of turning will be 1. Now the question are asking what will be the torque, maximum torque. So put the value of n over here, you will get the maximum torque, and it is L square IB over 4 pi. So this is the maximum torque, my dear students. Okay, so this was very fantastic question. Now we'll move for the next topic, or we'll solve. Okay, let me solve one more question. Okay, my dear student, let me solve one more question over here. All right, now this question is, or I will solve that question later on. I think we should proceed for one more topic. I'll give this question in group for your classwork. Okay, now oscillation of current loop in uniform magnetic field. As we know that if we'll leave a loop inside the magnetic field, it will start rotating, and if it is in its equilibrium position, and if you will disturb the coil by slightly, then it tried to regain its actual position. It means it will start oscillating. Okay, so oscillation of current loop in uniform magnetic field. Oscillation of current loop in uniform magnetic field. All right, the very simple thing, suppose you have suspended a coil like this one through which the current is flowing. All right, and its area, the mu, it is in this direction. If this is the magnetic field, all right, if you will disturb this coil, this coil is in this way, if you will disturb this coil and leave, it will experience a counter torque and try to be its actual position. If you disturb from here, it will try to be on its actual position, and due to its inertia, it must have some inertia because it has mass. Due to inertia, it will move little further its equilibrium position. Again it will try to, and it will face some counter torque, and it will move to its actual position. Due to torque, it will move slightly further. So in this way you can see it is oscillating in this way. All right, so we are going to find here the time period for this oscillation. Okay, if a magnetic loop is displaced from its equilibrium, loop will oscillate, remember. Okay, and it will oscillate due to restoring torque. What will be the restoring torque, my dear student? So the restoring torque will be minus mu b sine theta. Remember, when we talk about the simple harmonic motion, the theta should be very small. For SHM, theta should be very small. All right, it means sine theta will be prox equals to theta. It means tau restoring, you can write minus mu b theta, which is going to balance this mu b theta. Of course, you remember you have studied in standard 11 the I alpha, all right, minus mu b theta. Now I, the moment of inertia, so it is mu b over I theta. Try to recall this. Alpha is d2 theta by dt square, alright, minus mu b by I theta. Now you have to compare this equation by the standard equation of SHM. What is that? d2 theta by dt square, it is minus omega square theta. I hope you remember. It means omega square is mu b by I, alright, mu by I. Finally, thus omega can be written the root under mu b by I, and this is nothing but the 2 pi by t. It means the t will be 2 pi, will be reverse, so the I by mu b. In this way successfully we got the time period, my dear students. So the time period, if any conductor is placed in magnetic field, it will oscillate, okay, like simple harmonic motion, and the time period will be the 2 pi I by mu b, my dear students. Okay, so remember, I don't think this was very difficult, and any thing I should repeat, have solved this question in very fast speed, because you were knowing all the things. Okay, my dear student, in next lecture we'll start an important topic, that is the portion of your examination, and the question will be asked in 3 or 5 marks, and that is the magnetic field due to solenoid. Will start. Okay, the two things I'll teach you: the solenoid, if the solenoid is very long, that is of infinite length, okay, and the second thing, if the solenoid is of short length, that is the for the finite length. Okay, for both the solenoid we will do some work how to find the magnetic field, and also we will depict the pattern of magnetic field, how the magnetic field are oriented, okay, in that solenoid. So student, remember, I used to tell you, if you find any mistakes in my lecture, kindly notify in comment section, okay, so that it can rectify. Okay, my dear students, thank you very much.